In this video, I'm going to talk about simple harmonic motion, which is the repetitive movement back and forth through an equilibrium of an object. An equilibrium is just the center point. So this is best explained with a pendulum. I have a pendulum here when it's furthest up, and then this is when it goes through the center, so that's equilibrium, and this is when it goes up again. So a pendulum would swing from a point over there down to a point over here and go up again. So makes a curve. That pendulum would go back and forth. So I have a pendulum here in this position here. So in this position, the velocity of the bob at the end of the pendulum is 0. So the velocity is equal to 0, because if you think about it, it's not moving at all. It's staying in one place. And it's at this point at which acceleration is maximum. So if you think about it, gravity is acting at its best at this point because it's trying to push it the hardest over this side. So it's accelerating the most at this point. At this point over here, you're in equilibrium. So over here, I'll just write that's equilibrium. And at this point, the velocity is maximum. Because if you think about it, the bob would be going the fastest. So it'd be stopped over here because it goes up, it stops. It goes really fast when it goes down to here. And then it slows down as it gets to here again, and it stops. So at this point, which is here, the velocity is maximum, and the acceleration is 0. So it's not speeding up or slowing down at this point. And this point over here is furthest to the right. It's the same as this one. So at this point, velocity is equal to 0, and the acceleration is max. Okay, so this was simple harmonic motion on a pendulum. Now I'm going to go ahead and talk about what simple harmonic motion is like on a spring. So, for example, if you have a compressed spring, like here, the spring's compressed. When you let go of the spring is going to open up and go out to some distance. But then the spring would contract again, so it would go back to this position. This is also simple harmonic motion because if you think about it, if I draw it on a line, let's assume this is a compressed spring over here. When the spring is opening out, at this point the spring is stopped, but when it goes out to here in the middle, this could be our equilibrium point. At this point, like above, at the equilibrium, acceleration is 0 and velocity is maximum. So at this equilibrium point, the velocity is maximum and acceleration is 0. And when you come out to here again, the acceleration would be maximum, but the velocity would be 0, because if you think about it, the spring would stretch out all the way and then it would stop. But then it would be pulling itself back. And when it gets to here again, it'll get fast, the fastest it can be, and then it'll go back to being a spring. So simple harmonic motion can be represented on a line like this, where the middle is equilibrium, and these are the two ends. So we'll call this A and B. And this is the equilibrium point. So what all of this explains is simple harmonic motion. So to go back over simple harmonic motion, SHM, or simple harmonic motion, the equation for this is A is equal to minus kx, or you can write this as A is proportional to minus x. What you're basically trying to say with this equation is that the acceleration is directly proportional to the distance from the center. So if you think about it, when you're at the center, there's no acceleration, but as you get further away, the acceleration increases. And what this minus sign represents is that the acceleration is always towards the center. So A is proportional to minus x.